Start chapter 8 because there's not that much left in chapter 7. A lot of this stuff in chapter 7 is review of stuff that you already know. So do you feel like, oh, this is so much better than those crazy proofs? All right, so we've talked about functions and being one-to-one and being onto. So today we want to look at inverses of functions. So if a function with domain x and target y is a bijection, and remember, what is a bijection? What does that mean? It's one-to-one and onto. Okay, both of those. Okay, so if it's one-to-one and onto, then it's invertible. You can find its inverse, and you obtain that inverse by exchanging the first and second entries. So normally when you think about the function f, it's a bunch of ordered pairs x, y. The inverse will be the reverse of those. All the yx pairs. Okay, so if xy was in the function, then you swap. The yx will be in the inverse. And the idea is here is if you have a function f, you know, here's your domain x, and you pick something out of there. Okay, you put an x in, and then you get some y out. Okay, in your range, which is also the target because it's onto. And then your f inverse function, okay, does the opposite of that. It takes something here from the target of f and feeds it into the inverse, and then the inverse will tell you what x had to have been fed into the function to give you y as the output. Okay, so x will come out. So it's just does the opposite order, okay, of the original function. So one thing to note is that if we just had some random function and it wasn't one-to-one and onto, you might not get a well-defined function where everything from every value from your target, if you put it in, would always give you a value that comes out here. Okay, so the only way that you're going to get a well-defined function for an inverse over here is if your target and your range are exactly the same. So it has to be onto. Okay. And of course it has to be one-to-one as well, or you won't be able to invert this one. Okay. So there's the, if we just have a bunch of ordered pairs and that defines our function, then we would just, invert them all to get the ordered pairs for the inverse function. But if you're given a function that's some kind of algebraic kind of rule, that has an infinite number of ordered pairs in it, you can't just necessarily list all of the ordered pairs. You want some other way to write an algebraic expression to tell you what the inverse is. So, and this is something that you've all done before, so this will not be new to you. But let's look at the function f with domain real numbers, target real numbers, and we want to see if the function defined by take the input, multiply it by 2, and add 4 to it, does that function have an inverse? If so, what is the inverse? Okay, so probably if you were to look at this and show that it's one-to-one, we said that there was a test if we knew what the graph of the function looks like. So what is the test that we do to see if something's one-to-one? Yeah. That's to see if it's a function, but what if we want to see if it's, we do the horizontal line test to see if it's one-to-one. So that's the easiest way to check to see if something's one-to-one is graph it and see if it passes the horizontal line test. So graph and see if the graph passes horizontal line test. Okay, so what does the graph of this function look like? One of the easiest graphs you can ever draw. Exactly. So it's a line, and it has a y-intercept of 4 and a slope of 2, or like you said, yeah, it's like a vertical stretch of y equals x and a vertical translation as well. So however you want to think of it. But yes, you have this line that goes like this, right? Okay. And so if I take any horizontal line, no matter what it is, can it ever intersect that more than once? No. Okay, so it passes the horizontal line test. I'm just going to do HLT, horizontal line test, so I don't have to write that out again. Okay, so it's 1 to 1. And then to show that it's onto, I need to show that the range is actually the same as the target. Okay, so the range is the set of all the possible y values that can be, that we can get for this function. So we have a graph of it. It's pretty easy to see what the range is. What would the range of any line be? All real numbers. Okay, so the range is R, which is the same as the target. So it's onto. And then if we want to find the inverse, okay, there's a couple of ways that you may have learned to do this in the past. So one of the things is to write the equation as y equals 2x plus 4. Then swap x and y. So I'll rewrite that as x equals 2y plus 4 and solve for y. And so if we solve for y, we would get x minus 4 over 2 is y. And so whatever expression you get here, that's your inverse. So x minus 4 over 2, or if you wanted to write that so that it looked like a line, you could write that as 1/2 x minus 2. Okay, so that's option 1. Okay, you may also have learned to solve for x. Okay, this is option number 2. Okay, so on this one, I would do y, and then swap x and y. So I would put x here, and put y over there. So they're the same thing. Okay, just depending on who you learned it from, somebody may have told you to do it this way, somebody may have told you to do it this way. How many people swap first and then solve? Yeah, me too. I usually swap first and then solve. How many people solve and then swap? 2. Okay, it's 2 against 2, and the rest of you are like, I don't even know what you're talking about. All right, so hopefully you have done this at some previous time in your life. Okay. I know that I have high school students in Algebra 2 that do this, so I know that you've done this many times, and they do it in pre-calc, and they do it in calculus, so I know that you, in your lifetime, you've done it many, many times. Okay, so anyway, hopefully that's review, and it's coming back to you if you didn't remember how to do that. So I don't care, you can swap and then solve, or you can solve and then swap. It doesn't matter which way you do it, you're always going to get the same thing. Okay. And then this also should be familiar to you. So some functions don't have inverses, but we really would like them to have inverses. And so we restrict the domain on a desirable kind of function so that we can create an inverse for something that's like that function. Okay, so we'll look at a little bit of an example and then one that's even more familiar. So let's consider a function. Let's say it has domain, real, target, real numbers, f of x equals x squared, and we want to know, can we find an inverse? So in order to have an inverse, it has to be a bijection. It has to be 1 to 1 onto. Okay, so what does the graph of f of x equals x squared look like? That's a parabola, vertex at the origin, like this good old standard parabola. Okay, is that 1 to 1? How can we tell? Horizontal line test. Does it pass the It does not. Like, you can draw a horizontal line and it hits it twice. Like, lots of horizontal. The only one that wouldn't hit it twice was this little one at the vertex. Every other horizontal line is going to hit it twice. So it fails the horizontal line test. So it is not one-to-one. Okay, and so it doesn't have an inverse. Okay, but what if we really wanted it to have an inverse? Okay, so we would say, all right, well, that doesn't have an inverse, but can I take part of that function and just like restrict my domain to something that would pass the horizontal line test, and then just have that part that's invertible? Okay, and so if I say, all right, so all of these, I can't have both sides of this parabola because then it's going to fail the horizontal line test. Yep, sorry. But if I just started here and just took this part of it, just what's in red, and I took away the part that's in purple over here, so I'm restricting my domain to be x values that start at 0 and then go on to infinity. So if I restrict the domain, and I'm just going to call this R, not a fancy R, just a plain old R. Okay, the set of x that's real numbers such that x is greater than or equal to 0. So if I restrict the domain to be just that part of the set of real numbers, just the values that are greater than or equal to 0, okay, then if I take that away, what I'm left with in red, will that pass the horizontal line test?
Yes.
Yes, that will. And so that part of it is invertible as long as I make it one-to-one and onto. So I actually have to restrict the range or the target as well. Okay, so what would I have to make the target so that this would be onto? Same thing. So this is to make the function onto, and this is to make the function one-to-one. Okay. So we've restricted the domain, actually, and the target, and the range, or and the target, so that the resulting function is a bijection. Therefore, it will have an inverse. Okay, and the way that we find the inverse is just the previous steps that we looked at. We would write this as y equals x squared. Then we would swap x and y, so I turn this into x equals y squared, and then solve for y by taking the square root of both sides. Okay, and we would just do the positive square root, not the negative one, because we only, in our, we want to make sure that we're going to be in these sets of positive values. So don't worry about the plus or minus in front of that. Normally you would probably think, oh, I should put plus or minus in front of this, but we need to make sure that we're in these sets greater than or equal to 0. Okay, and so my inverse function f of x would be the square root of x. And that's only if I restrict the domain to be x values greater than or equal to 0 and the target range to be y values that are greater than or equal to 0. Then I can get an inverse. Okay. The other place that you've probably seen having to restrict the domain that you're very familiar with is the sine function and the cosine function. And then we could even do tangent, but we'll just do sine and cosine for now. So if you think about the way the graph for sine and cosine, you know, it kind of, sine goes like this, right? So if you look at the sine, is the sine one-to-one?
No.
Absolutely not, right? And so the sine doesn't have an inverse. Okay, but if you go on your calculator, there's a little sign with a little -1 in it that looks just like this thing on it. So your calculator thinks it has an inverse. Why is that? Well, that's because we've actually restricted the domain. Does anybody remember what we restrict the domain to so that we can actually do an inverse sign? Yep, -pi/2 to pi/2. So from there to there. So it's this part that we restrict to. Okay, so as long as we restrict the sign to only go from -pi/2 to pi/2, we get every value we need from -1 to 1. Okay, and that little part that I've put in red passes the horizontal line test, so that part of it is invertible. And we just throw the rest of it away. Okay, cosine, similar kind of issue, just the restriction. Maybe I should put this. Okay. Restrict domain to -pi/2 to pi/2. And then cosine looks very similar, except it goes like this. Okay, also does not pass the horizontal line test, does not have an inverse. But if I restrict the domain, then I can make it invertible. Okay, and so for the cosine, where do I restrict the domain to make it invertible? Yeah, this one is 0 to pi. So this one goes from 0 to pi right there. Okay, and that would give me every value is covered from -1 to 1. Okay, but I just restrict it just to the red portion. That will pass the horizontal line test, and I'll be able to find the inverse of that one. So for this one, we restrict the domain to 0 to pi/2 to pi. Sorry. Okay. So those are familiar examples that you've seen where you've had to do restrictions on the domain in order to make something invertible. Okay. All right. And the last thing we want to look at to finish up our discussion on functions is the composition of functions. Okay, so let's say we had two functions. F goes from x to y, and g goes from y to z. Notice that these two have to match each other. Okay, so if I want to find the composition of g composed with f, or g of f, we're going to do the f function first here. Okay, so the input is going to come from the set x. Okay, and then after we do the f, it will give us some value. We'll feed that into the g function. Okay, so that f will give us something from y. We'll feed that y value into the g function, and it'll give us an output from z. And so our g composed with f will have a domain that matches f's domain and a target that matches g's target. Okay. And the way we define that is, okay, we just take the input, we put that into the function f, and whatever output that gives us gets fed into the g function, and we compute g of whatever that value is. Okay. And you probably know that in general, if you do f of g and g of f, they're not going to get the same thing in general. Okay. There are some, if they're inverses of each other, you'll get the same thing, but not in general. Okay. But, so it's not commutative, but it is associative. So if you compose more than one function, okay, it doesn't matter what order you compose them in, you always get the same thing. So if you do f of g of h, that will be the same thing as f of g of h. So those will both give you exactly the same thing. It'll always be h, feed the input into h, whatever output you get on that one goes into g, whatever output you get on that one goes into f. Okay. So we'll look at examples, and this isn't a proof, but we'll at least convince ourselves that for these functions that it happens. All right, so let's first of all look at f of g. Okay, so if we want to find f of g, it's the function on the right that's going to always get fed into the function on the left. Okay, so this one's going to be f of g of x. So we're going to take whatever g of x is, so x squared minus 1, and use that as the input to our f function. Okay, so when we take x squared minus 1 and put that in as an argument to our f function, then this argument here, x, will get replaced with x squared minus 1, so this will become x squared minus 1. I'm just going to put parentheses around that. That replaces our x, and then minus 2, so that simplifies to x squared minus 3. Now, if we did g of f in this order, so this time we're going to take the f function, or the expression x minus 2, and use it as an input to our g function. So our argument here of x is going to get replaced with x minus 2. So in our g function, this will be x minus 2, and that will get squared. And then we'll subtract 1 from it. So this one will be x squared minus 4x plus 4 minus 1, or x squared minus 4x plus 3. So notice, as we expected, these aren't the same. And generally that's true. F of g and g of f are not going to be the same. But we are expecting f of g of h and f of g of h, or f of g of h and f of g of h to be the same.
Can you show me like the arrows way, how like f of g, h, like how each one goes in? You said g goes into f, f goes into g, and then there's two, see what I'm talking about?
Yeah, so if I have, so the arrows way, you mean like if I have like a little box and I feed?
Well, you literally like hand motion g goes into f, so like could you do that with like f of? I think it's like
Yeah. So, yeah, so G, that's why, so putting it in here, you can see that G is going into F, right?
But I mean for the third one. So I understand when it's just 2, but when it gets to 3.
Oh, okay. So, imagine this, because there's parentheses here, I'm going to have a function, f of g. And that's this function up here. Okay? So, this is going to be f of g, and then I'm going to put h of x into it. Okay, so here's h of x, which is 3 minus 2x, and I'm going to put that into the argument of f of g. So here's f of g, which is x squared minus 3. So I'm going to put h of x, this, in for the argument over here.
Okay.
Does that make sense?
Yeah.
Okay, and so here's my f of g, so I have to square whatever the input is. My input is 3 minus 2x. I'll square that. And then I subtract 3 from it. Okay, so that's just taking my h of x function and using it as the argument to my f of g, which I computed up here. Okay, so that one's going to be, what, 9 minus 12x plus 4x squared minus 3. And if we write that in standard form, that's 4x squared minus 12x plus 6. And then if we do f of g of h, okay, we don't have g of h yet, so let's do that one first. So g of h, we're going to take the h function and put it into g. Okay, so here's our g function, and we're going to take h as the argument and put it into the g function. So we're going to take 3 minus 2x and use that as the argument to g. So we're going to square 3 minus 2x and then subtract 1 from it. So that will be our same, this is going to be 9 minus 12x plus 4x squared minus 1. So this is our 4x squared minus 12x plus 8. And then we're going to use that as an argument to the f function. Okay, so in our f function, that's take the input and subtract 2 from it. So the input is our g of h function, so that's our 4x squared minus 12x plus 8. And then we're going to subtract 2 from it. put parentheses around this so you can see that's our x. We just replaced x with that argument. And this one is 4x squared minus 12x and then plus 6. Exactly the same. So these are the same. And no matter how many of those we had, even if we had like 5 of these functions strung together and we did them in any order, they're always going to turn out to be the same. Okay. So usually, try to do the easiest ones first, if you can. Okay. Is that good? Any questions on that one? Good. Yep. Okay. Then we have the identity function, which maps every set and every element in a set onto itself. Okay, that's what the identities always do. They always map. If you think about the identity operator for addition, you add 0. Why? Because that gets a number back to itself. The identity for multiplication is to multiply by 1. Why? Because that gets a number always back to itself. Okay. And we looked at identities for and or. What's the identity for and? You and with what? To get a thing back to itself. This is good review.
What?
Yeah.
Can you say that again?
Yeah.
Visuals, I'm sorry.
All right, so we have like the identity property of conjunction. So if I take anything x and I and it with something, and I want to get x back, what do I have to and it with?
True.
With true. We have to and it with true. Yeah. This is okay, the identity operation for conjunction. What about disjunction? If I have x and I or it with something to get x back, what do I have to or it with? What's the identity operation for disjunction? It's false. Yep, it's false. You're right. Okay. So you've seen lots of identity operations before. Even in this class, we've talked about identity operators. Okay, so this is the identity function. It just takes some input, and then it's the function that if you put x in, you get x out. That's what makes something an identity. Okay, is whatever you put in, that's what you get out. All right, so the identity is just marked, and you've kind of hear some of you are taking like linear algebra, right? So you know what the identity matrix is. Go with all those ones, because when you multiply it, you just get the matrix back, right? So you have seen lots of identities. All right, so just the capital I denotes the identity, and then the subscript tells you what set we're talking about. So an identity function on set A will map any element in A back to itself in A. Okay, an identity function, if I had a subscript B there, then it would take inputs from the set B and map them back to B on itself. Okay, so if I have a function f with domain A and target B, and it has an inverse, okay, so imagine the inverse is going to go from B to A. So if I do a composition of functions, f inverse composed with f, I'm going to get the identity function on A. If I do it in the other order, okay, if I do f composed with f inverse, I'm going to get the identity on B. So let's think about what's happening here. So here, f is the thing that happens first, right? Because I'm doing f inverse of f of, I'll just call this A. So the f function happens first. It's on the inside. So f starts with A, and then it gives us something in B. And then whatever value we got from B is going to get fed into the f inverse function. So that goes from B and gives us something in A. Okay, so notice the input will come from A, the output will be in A, and so what we're getting is the identity on A. However, if we compose them in the other order, so this time we're doing f of f inverse. of, say, B. Okay, so F inverse is the thing that's on the inside. That's happening first. So we're going to take a value from B, and it's going to give us something from A. And whatever output it gets us gets fed into the F function. Well, that takes something from A and gives it to B. Okay, so in this case, we get an input from B, an output from B. This is giving this the identity on the set B. Okay, so in either case, we're getting an identity. It's just on a different set. Okay, now if you probably most of the things that you've seen like go from real numbers to real numbers, and so you never really distinguished maybe that you were getting something different because always your domain and your range are probably the same. But if they are different, they're going to give you two different identity functions. Okay, this one on A, this one on B. Okay. So this example, we've got just lots of little things to look at. So here's our function. It's just a mapping. Okay, we see that the function has a domain of A, B, C, and a target of 1, 2, 3, 4. It's not onto. I already answered that question for you. Pretend I didn't say it. Okay, I'm going to ask you. And then we got H from a domain 1, 2, 3, 4 to the target W, V, X, Y, and I'll let you decide about this. Okay, so going to G, what is the range of G? 2 and 3.
2 and 3.
The set containing 2 and 3. Very good, Ben.
Thank you, I'm putting on the draw.
What is the range of H? WVXY. Okay, so is G onto? So wait, first of all, is G 1 to 1? No, it's not 1 to 1. What's the issue with G?
B and C are both mapped onto 2.
Yeah, B and C are two different values that map onto the same number 2. So it's not 1 to 1. Is it onto?
No.
No, I already spoiled that for you. Okay, and why isn't it onto? What was it?
1 and 4 don't have anything mapped.
Yeah, because 1 and 4 don't have anything mapping to them because the range is not equal to the target, right? Okay. So range is not equal to target. And that's how we can tell. Okay, how about H? Is H 1 to 1?
Yes.
Yes, it is. Is it onto? Yes. Okay. All right, and so if we were to look, is G going to be invertible? No, because it's not a bijection. It's not 1 to 1 and onto. Is H going to be invertible?
Yes.
Yes, that one will be. Okay, so let's look at, if we just are given arrow diagrams like this, and we want to figure out what H of G of A is. Okay, so we're going to go to the one that's closest to A. Okay, this is just, think of this as H of G of A. So we're going to do G, okay, and give it input A. So we're going to go to G, give it input A, and it maps to 3. And then we're going to take the 3 and give it to the H function. And so when we give 3 to the H function, what is the output going to be? Y. Okay. How about let's do H of G of B? Okay, so G of B is 2, and then H of 2 is W. And how about H of G of C? So G of C is, and then H of 2 is W. Okay. Because this one is not 1 to 1, we get this same value here. All right. Does G of H of 1 exist? So let's see. What is H of 1? X. What is G of X? That's undefined, right? So X is not in the domain of G. So this is no, X not in domain of the function G. So remember, in order for us to be able to compose two functions, the target of H would have to match or be the same as the domain of G. And here, the target of H, which is WVYX, and the domain of G, ABC, are not the same. Okay, so if those are not the same, we can't compose the functions. Okay, so target H not equal to domain of G. Okay, now we already said that H is 1-to-1 and onto, so it's invertible. So if I wanted to draw an arrow diagram, what would I list on the left-hand side as my domain values for H inverse? WVXY. And then on the right for my target values, I would have 1, 2, 3, 4. Okay. And then what would W map to? 2. And V maps to 4. X maps to 1. And Y maps to 3. Okay. So let's find H of H inverse of X. So we would do H inverse first. So first we do H inverse of X, which is 1. And then give 1 to the H function and we get X. Okay. Which is good. We said that we should, these are inverses of each other. We should get the X back. I mean, you can guess what this one is. 3. But let's verify it with the picture. Okay, so when I do H of 3, I get Y, and when I give Y to H inverse, I get 3. Okay, so indeed it is 3. Okay, it would be bad. We would have done something wrong if we didn't get that. Okay. All right. So that wraps up our discussion of functions. Yay. But that doesn't mean we're done. Okay, we're going to do chapter 8, but we're not going to do all of it today. There's lots of fun stuff in chapter 8. And then after we're done with chapter 8, we're going to do as much of chapter 12 as we can, and then we'll just be done. Okay, so we're going to skip what's in between those. On counting and probability, you'll do all that stuff in your statistics class anyways. Okay. Okay, so the first thing we want to look at is the division algorithm, which isn't actually an algorithm, but it leads us to an algorithm. Okay, so the division algorithm is actually a sort of a theorem that tells us that if we have n and it's any integer, and d is a positive integer, then there are unique integers q and r having to be between 0 and 1 less than this number d, such that we can all write n equals q times d plus r. Okay, this is something that you've known ever since you were in like 3rd, 4th grade and you learned how to divide numbers. So think about way back if you can remember, and you were doing like when you were a little kid and you were doing like 24 divided by 7. Okay. And you said, all right, well, 7 goes into 24 3 times, and then you wrote this, and you subtracted. I hope this is how you learned, maybe not. Okay, and then maybe you wrote a little remainder of 3. And then if you had to check it, the way that you would check it is you would say, okay, is this number 24 equal to the product of my divisor times my quotient, or in this case, they're doing quotient times divisor, so about 3 times 7, and then you have to add on the extra, the remainder, and then you say, oh, that's 21 plus 3 is 24. Yep, I did it right. Okay, so we've known for a long, long time that if you take a number, that will be equal to the quotient times the divisor plus the remainder. That's all this means. Okay, so Q is quotient, D is divisor, R is remainder. Okay, so this is your divisor, Q is your quotient, R is your remainder. And the division algorithm is just a theorem that says no matter what n you choose, I can always break it up this way. Okay, so for example, let's say we have the number 16. Okay, I want that to be some quotient Q times my divisor of 3 plus some remainder. So what would I put in for my quotient? 5. And what would my remainder be? 1. Okay, so here our Q is 5 and our remainder is 1. Now this gets a little bit tricky when we go to negative numbers. So imagine I have negative 27. I want to write that as some quotient times the number 7 plus a remainder. Should we put in here for the quotient? Okay, so negative 3. Let's not write that in because that's what you probably guess. If I put negative 3, I'll get a negative 21, and then what would I have to add? I'd have to add negative 6. Okay, now let's go back and look at this. R, the remainder, must be between 0 and d minus 1. So our remainder has to be between 0 and 7. So if I put negative 6 there, is that between 0 and 7? No. Okay, so it's super tempting to want to put a negative 3 in there, but we can't do that because that will not give us a positive remainder. So what should we put? Let's write this down here. Negative 27 equals negative 3 times 7 plus negative 6. Okay, this won't work because negative 6 is not between 0 and 7.
Is it 7 or is it 6? Because it says D minus 1.
Yeah, so 0. So between, so that would be, yeah, so 0 and 6 inclusive. Okay. I'm thinking like less than 7, which is equal to 6. Okay, so that one won't work. So what really should we put in here for our quotient? We'll put negative 4 in there. So that would be a negative 28, and then what would our remainder be? 1. Okay, so this would give us a Q of 4 and a remainder of 1. Okay, and if you've ever written programs in, C, Java, C++, and you've ever used, integer division or a mod on a negative number, you've seen this thing, and you're like, what's it doing? That's what it's doing, okay? So that's how your mod and div operators will work in your programming languages, because the quotient is always the result of the div, like a integer division, and the R is always the result of your modulus operator, so your like percent operator. Okay, which takes us to our next slide. So the div and mod operators produce the quotient and the remainder that we just looked at. Okay, so we'll always get the Q value will be the result of the div operation. The mod operation will always give us the remainder. So if you were in a programming language and you did 15 div 4, okay, so in Java or C++, that's just if you had 2 integer operands and you put a slash in between them, it defaults to integer division. It'll always give you the quotient, right? Okay. And if you do it in Python, you got to do a double slash there to get it to do integer division for you. But every language has this operator in it, either as a default or you can choose it. Okay, so what would you get for 15 div 4? You get 3. Okay, and then we've got the tricky one. How about negative 13 div 4? So is it negative 3? So 4 times negative 3 is negative 12. And what would I have to add as a remainder? I'd have to add a negative 1. Okay, that's not going to work. Okay, so it's not negative 3. It's going to be negative 4. Okay, because we're going to have 4 times negative 4 plus 3. Okay, you have to have a positive remainder there. Okay, so the negative ones are the tricky ones. Okay, and so then if we did 15, then mod 4, that's going to be 3. And then negative 13 mod 4 is also 3. You can see is our remainder over there is 3. So you could try those out in Java or C++ or C or whatever your programming language of choice is, and you'll see that's how they work there. Okay. So we call this the division algorithm. Really, it's just like a theorem that tells us we can always write this, but there are actually some algorithms that we can use to give us the Q and R values, and we'll just trace through these algorithms for our little examples here. Okay, so this one right here is what the little piece of code or algorithm that we would have to run if we have a positive number, like n equals 15. And this over here, we would have to run if we have a negative number, like our n equals negative 13. Okay, so if you think about it, we're just doing division, and multiplication is repeated addition. Division is repeated subtraction. It's like the opposite of that. So what you'll see here is we're just doing repeated subtraction over and over again to figure out how many times our divisor will go in. Okay, when we have a negative number, we're repeatedly subtracting a negative number, which is repeatedly adding something. When you subtract a negative number, you're adding. Okay, and that's why there's the difference here. Okay, because here our repeated subtraction is we're subtracting a negative number. Okay, so let's just run through this. So we've got Q is 0, and R always starts out as n. In this case, this is our n value is 15. And then our D value is 4. So as long as R, which is currently 15, is greater than or equal to 4, which is true, then we're going to come in here and we'll increment Q. So this will become 1. And then we'll take the R value and subtract D from it. So we'll subtract 4, and this becomes 11. Okay, and then we go back and check our condition. Well, our current value of 11 is still bigger than 4. So we'll increment Q to 2, and then subtract D from R. So this goes down to 7. And then we'll check our loop condition again. 7 is still bigger than 4. So we'll increment this up to 3, and then subtract, and we'll get 3. And then we'll come check our loop condition. Our R value is 3. Is that bigger than or equal to 4? No. And so we'll exit the while loop. And then we're going to get done. Our Q value is 3, and our R value is 3, just like we would have expected. So the quotient, so 4 goes into 15 3 times with a remainder of 3. So we're just subtracting off 4 as many times as we can, and then this is what's left over when we can't subtract any more 4s. Okay. If we started out with a negative number, so we'd have Q is 0, R starts at negative 13, and our D is still 4. So as long as our remainder is less than 0, as long as we have a negative number here, we got to keep adding, okay? Because we can't have a negative remainder. We've seen that. So we'll come in here, and this should be a Q equals Q plus 1. I don't know why that says minus. There must be I just cut that right off the screen, but that should be a 1. Oh, no. No, it is a minus because it has to be a negative number. I'm sorry, it's good. So we need a negative quotient. Okay, and then R is R plus D. So when we add 4, we get negative 9. And then we'll come back around here. Okay, a negative number is still less than 0. So we subtract from our quotient because we have to have a negative quotient. It'll now be negative 2. And then add 4, this will become a negative 5. We've still got a negative R value, so we'll go back into our loop. This becomes negative 3. Okay, we add, this becomes negative 1. That's where we're tempted to stop when we just do this, but if we run the algorithm, we're not tempted to stop there because we see that that's a negative value. This becomes negative 4. And then we add, this becomes 3. Our R value is no longer negative. It's greater than 0, so we stop, and our quotient value is -4, and our remainder is 3, just like we expected it to be. Yes. So just like we had back here, this Q and this R. Okay. So we can use modular arithmetic. There's lots of different applications for it. I don't know if we'll get to the fun ones today. Maybe not. We won't. That's okay. We'll get to them after Thanksgiving. So modular addition and modular multiplication are used a lot. And what they're good for is if you have some kind of a set, okay, and you use either modular addition or modular multiplication, and you always do mod of however many numbers you have in your set, you're always going to get back to a number that's in your set. So for example, notice I've got 5 numbers, 1, 2, 3, 4, 5. If I divide by 5 and take the remainder, it's always going to be a number that's less than 5, 0 through 4. Okay, so if I always apply the mod operator to whatever operation I do, I'm always going to have my output go back to my original set. So even if I do 2 plus 4, that's 6, which takes me outside of this set. But as soon as I do mod 5, well, 6 mod 5 is 1, and it puts me back in the set. Okay, multiplication, if I do 2 times 4, that's 8. It takes me out of this set. But if I do 8 mod 5, that's 3, and I'm back in the set. Okay, so this modular arithmetic is a way for me to guarantee that my result is always back in the original set where my operands came from. Okay. And it's very handy for lots of different applications. Okay. Mathematically, so if you were ever to take a course in abstract algebra, which I doubt any of you ever will, unless are any of you going to be math minors or double majors in math? No? Okay, so anyway, so if you took an exciting abstract algebra class, you would learn all about this kind of stuff. But for now, we'll just tell you that when you have a set 0 through m minus 1, and how many elements are there if I start with 0 and go up to m minus 1? How many different numbers is that? M, yeah, m different numbers. Okay, so there's m of them. So if I take those numbers and I always do addition and multiplication and then do mod m at the end of it, which puts me back into that set between 0 and m minus 1, that's a closed mathematical system, an algebraic system called a ring. It has a special fancy name. And we denote it by z and then a subscript with however many elements we have in that m value. Like so for z3 would have the element 0, 1, 2 in there. z7 would have 0 through 6. z10 would have 0 through 9, etc. Okay, so it's integers that are 0 through 1 less than my subscript here. Okay, and then I always define operations in that system by always doing mod whatever that subscript is at the end. So, for example, if I want to do addition in Z3, so Z3 has 0, 1, and 2. Those are the 3 symbols that it has. So, let's say I wanted to add these. I can make myself a little table here. And this will be addition. Okay. So if I want to figure out what 0 plus 0 is in the ring Z3, I do 0 plus 0, take the result, and then do it mod 3. Okay, so 0 plus 0 mod 3 is 0. Okay, 0 plus 1 mod 3. 0 plus 1 is 1. 1 mod 3 is, what's the remainder that you get when you take 1 and you divide it by 3? How many times does 3 go into 1? 0 times. Okay, and then a remainder of 1. Yeah. Yeah, I know. It's like you have to wrap your brain around it. Okay, let's try another one. 0 plus 2 is, and 2 mod 3. 2, yeah. So 3 goes into there 0 times with a remainder of 2. Okay, how about 1 plus 0 in this ring? 1, good. So 1 plus 0 is 1, and 1 mod 3 is 1. Then 1 plus 1? 2. Okay, so far, everything acts just like we expect. Now we're going to get to something tricky. So 1 plus 2 in this ring. So the answer is going to have to be something in here. So normally I think that 1 plus 2 is 3, but I've got to do 3 mod 3. 0. Okay, so in the ring Z3, 1 plus 2 is 0. 2 plus 0? 2. 2 plus 1? 0. And 2 plus 2? 1. Because 2 plus 2 is 4. Okay, that's going to be 2 plus 2 mod 3. Okay, this one is 2 plus 1 mod 3. That's where we're getting those values from, right? So those ones, those are the tricky ones. And this one right here is another tricky one. This one, 1 plus 2 mod 3. Okay, so that's addition. And then how about multiplication? Let's try that. When I took abstract algebra, my professor, Professor Zweer, when we would be doing things like this, he would say, oh, he would run over and he would close the door and he would say, in case any freshmen are walking down the hall, we don't want them to hear this, that 2 plus 2 is 1, you know, like he would. So he was a funny guy. All right, so here we're going to do the same thing. One of these will be easy. 0 times 0. 0 times 1. 0 times 2. Okay, those ones are easy. Still, when we multiply by 0, we get 0. Okay, 1 times 0. Okay, 1 times 1? 1, yes. 1 times 2? 2, still 2. 2 times 0? 2 times 1? Okay, and really the only tricky one, 2 times 2 is 1. Okay, so 2 times 2 is 1 because we're doing 2 times 2, but then we're doing mod 3 at the end. The remainder is 1. Okay. So the precedence of the mod and div operators are exactly the same as the precedence of multiplication and division. So if you've ever used, you know, the percent in programs that you've written, you've probably figured that out as well. So it happens in the same, with the same precedence as multiplication and division. So remember that multiplication and division have higher precedence than addition and subtraction. Okay. And then when you have only multiplication and division, everything is done from left to right. Yes, it's PEMDAS, exactly. But PEMDAS, so MOV and DIV are part of your M and Ds. Yeah, so M can stand for multiplication and mod, and D can stand for division and div. Okay, so same thing as PEMDAS. All right, so in this, if I have 2 plus 5 mod 6, what has the highest precedence? The mod. So 5 mod 6 is going to be done first. Okay, so this is done first. And so we're going to get 2 plus, and what is 5 mod 6?
0.
How many times does 6 go into 5?
0.
0 times, with what is your remainder? 5. Okay. So that's going to be 2 plus 5, which is 7. However, if I put parentheses around the 2 plus 5, now my parentheses change the precedence. And so the 2 plus 5 is done first, and this will become 7 mod 6. And 7 mod 6 is 1. Okay, so parentheses important. Okay, how many programs have you written where you didn't put parentheses and then it took you like hours to debug it because you should have had parentheses there? Sometimes you just, even if you know, just put parentheses. All right, this one, 2 times 5 mod 6. What will happen first?
5 mod 6. 2 times
So 2 times 5, because the multiplication and the mod have the same precedence. Whenever you have the same precedence, it goes left to right. So you have to go left to right. So if I'm going left to right, the first thing I come to is the times. So the multiplication will happen first. This will become 10 mod 6, which is 4. Okay. And so really it's exactly the same as if I would have put parentheses there. Okay. So this will also be 10 mod 6, which is 4. If I want the mod to happen first, I would have to put the parentheses around the 5 mod 6. Okay. How about the 3 plus 4 div 3? What will happen first?
The div.
Yeah, the div will happen first. So we're going to get 3 plus, and what is 4 div 3? 1. Okay, 3 goes into 4 one time, so that will be 1. So this will be 4. But if I put parentheses around the 3 plus 4, I'll do that first, and I'll get 7 div 3, which is 2, because 3 goes into 7 twice. Okay. The next one, what happens first? The multiplication. So this will be 12 div 3, which is 4. Okay, which will be exactly the same as the one on the bottom. So this will be also 12 div 3, which is 4. All right, I think that's a good place to stop. And we will look at fun applications next time. So enjoy your Thanksgiving. Eat lots of pie and turkey.